Have you ever tried to sit in a chair at the same time as someone else? Or had someone break the chair completely? That's basically how enzyme inhibition works. Welcome to competitive versus non-competitive inhibition, understanding how enzymes can be stopped or slowed down. Enzymes are biological catalysts, proteins that speed up chemical reactions in your body without being used up. Inhibitors are molecules that slow or stop enzymes. They're crucial in regulating metabolism and are also used in many drugs. In competitive inhibition, the inhibitor competes with the substrate for the enzyme's active site. It's like two people trying to sit in the same chair. Only one can fit at a time. The more substrate you add, the more likely it will outcompete the inhibitor. Scientifically, this means the enzyme's Km increases. It needs more substrate to work efficiently, but the Vmax stays the same. Malonate competes with succinate for the enzyme succinate dehydrogenase in the Krebs cycle. When malonate binds, it blocks succinate from turning into fumarate, slowing down cellular respiration. So, competitive inhibitors are like temporary blockers. They don't damage the enzyme, just occupy it. In non-competitive inhibition, the inhibitor binds somewhere else on the enzyme, not the active site. It's like someone cutting the chair's legs. The chair is broken even if the seat is empty. This changes the enzyme's shape and stops it from working, no matter how much substrate you add. A classic case is lead ions bind to ferrochelatase, the enzyme that builds heme, the red pigment in blood. When lead distorts the enzyme's shape, heme synthesis stalls, causing fatigue and anemia. Other metals like mercury and arsenic act similarly, binding permanently and denaturing vital enzymes. Here, fewer working enzymes remain, so Vmax drops. The enzyme's speed limit lowers, but Km stays the same. So competitive inhibitors just take the seat, but non-competitive ones break the chair legs for good. Understanding this helps doctors prevent metal poisoning and design drugs that block enzymes safely. Let's summarize both inhibition types side by side. Competitive binds the active site, direct competition. Non-competitive binds elsewhere, changing shape. Competitive inhibition is reversible by adding more substrate. Non-competitive isn't. It changes structure. Competitive, Km increases, Vmax unchanged. Non-competitive, Km same, Vmax drops. Cells naturally use inhibitors to control metabolism, switching reactions off when enough product exists. ATP inhibits phosphofructokinase in glycolysis, slowing sugar breakdown when energy is abundant. Medicines use controlled inhibition too. ACE inhibitors relax blood vessels to lower blood pressure. Sulfa drugs mimic bacterial substrates, competitively blocking folate synthesis to stop bacterial growth. Some cancer drugs are non-competitive inhibitors, turning off enzymes that trigger tumor cell division. Let's quickly recap what we've learned: how enzymes speed up life's chemistry and how inhibitors can control or block them. In competitive inhibition, molecules like malonate compete for the enzyme's active site, blocking the real substrate, just like two people racing for the same chair. In non-competitive inhibition, like with lead and ferrochelatase, the inhibitor binds somewhere else, changing the enzyme's shape so it can't function, like cutting the chair legs. Remember the kinetic effects. Competitive inhibition increases Km but keeps Vmax the same, while non-competitive leaves Km unchanged but reduces Vmax. These ideas explain how drugs work, how toxins act, and how cells self-regulate. Enzyme inhibition is the language of both medicine and metabolism. Here's a trick to remember. C for competitive, chair competition. N for non-competitive, not fixable once the enzyme's shape changes. So overall, enzymes speed up reactions, Inhibitors slow them down. Competitive fights for the seat. Non-competitive breaks the shape. Both are vital for controlling biochemical pathways.
Thank you so much for watching and learning with me. I'm Shlok Patel. This video was created as part of our biochemistry project to help explain enzyme inhibition in a clear, visual way.